Hello everyone, this is Uday and welcome to Uday Lectures. Many of us have problems in solving data structure problems, particularly a tree data structure. We get so many confusions in how you perform different operations on tree data structures. In this video, I am here to help you out in understanding AVL tree operations very clearly. So in this video, we are going to focus on the deletion operation in AVL tree. I've already made a dedicated video for AVL tree introduction and how you can perform insertion operation in AVL tree. And it is really important to understand a binary search tree data structure before we get into the AVL tree, because AVL tree is an extension of binary search tree, and to overcome the problem of time complexity in binary search tree in a worst case scenario, we have got into something called AVL tree. So it is really important for you to understand binary search tree data structure before we dive into the topic of AVL tree. So why delay? Let us dive into the topic. AVL tree deletion operation works like this. So the deletion operation is performed similar to the rules of binary search tree, and that is why I said it is really important to understand binary search tree first before we dive into the AVL tree. So to perform a deletion operation in AVL tree, so there are different scenarios, like we can delete a child node directly without making any rotations or without making any swapping operations. And if it is an internal node with single child, then we have to replace that internal child with the internal parent node with the child node, and then perform the deletion operation on child node. And if it is a parent node with multiple childs or multiple or longer subtrees, then we will end up in swapping that with the in order successor. So these steps I have already explained in the binary search tree operations, where I have made a video on binary search tree deletion operation. Do watch that video. You will be notified with the video also. And if you understand binary search tree deletion operation, it is really easy to understand AVL tree deletion operation also. And what exactly is the difference between binary search tree and AVL tree is that the balancing factor. So after we perform any deletion operation in AVL tree, it can be a child node, or it can be an internal node, or it can be any node. So we have to recalculate the balance factors for all the nodes, because height of the tree is impacted. And after you compute the balance factors, so we should check the unbalanced nodes right from the deleted node to the top node, which is root node. And we will be performing rotation operations to try and balance the deleted or the affected nodes. And we have different rotation operations in AVL trees, like we have left rotation, right rotation, left right rotation, and right left rotation, which we call as combinational rotations. And we can perform any of the required rotations according to the situation in the according to the situation in tree, to balance the tree. So let us dive into an example problem, and we will try and understand different rotations and different situations we come across in performing the deletion operation in AVL tree. Let us dive into the example problem now. Here I have considered a AVL tree deletion problem, and I have considered this example because I have included all the possible rotations and all the possible situations that we come across in AVL tree deletion operation. And let us go ahead and try solving this problem. So here we have a present tree which is given to us in the problem, and we have been given with the list of numbers, and we are asked to perform deletion operation on this particular numbers, right? And do remember, so the deletion operation should be performed only on the updated tree. So for example, if I have to delete 85, this is the present tree, I can go ahead and delete it, and then check the balance factors, and then try performing the rotations to balance the tree, and then try deleting the next node, which is 91, on the updated tree. So here I have this tree, so let us go ahead and try delete 85, right? Deleting 85. Also remember, in exams they will not be giving you balance factors sometimes in the tree that they give also. So what you should do is you should try and find balance factors by yourself on them. So it is very simple and easy. I have already explained that in the AVL tree video which I have already recorded. You can watch that video to understand that better. Okay, so here the leaf nodes will have the balance factors of zeros. And here if you see the left and right subtree, there are equal number of or equal heights of subtrees. So the balance factor for this also becomes 0. And whereas here we have 2 in the left subtree and 2 levels in the right subtree, so the heights will be 2 minus 2, which is 0. And whereas for 70 it is 3, the deepest leaf nodes are this. and here it is 2. So 3 minus 2 will become 1. So these are all the balance factors, and the simple rules must be followed as they are. So the balance factor should always be between -1, 0 and 1. So these rules must be followed no matter what we perform in the AVL tree. Okay, now let us go ahead and try deleting 85, right? So to delete 85, we can see here that 85 is the leaf node. So according to the binary search tree operations, we can perform deletion operation directly if that is a leaf node, and if it is not having any children, or if they are not having any child nodes. So now I can delete 85 directly. So right from here, I can delete 85 directly, right? So let us go ahead and reconstruct the binary search, the AVL tree after performing the deletion of 85. Okay, so 70 stays as it is, and 35 stays as it is, and all this, the entire subtree stays as they are, because we are not performing any operations on this side of the tree. So which is 40 here, and then we have 60 here, and here we have 91, and 85, since it is deleted, we should not be involving that or including that in the tree here. So now we have deleted 85 from the tree, and now it is the next step in AVL tree, which is really important, which is we calculating the balance factors. And just like I said, the leaf nodes will have the balance factors of zeros, and for this it is 1, and for this it is 35 is having two left subtree, two levels of left subtree and two levels of right subtree, so it will be 0 again. So for this it is 3 minus 2, which is 1 still, and for this it is, so it was empty in the left subtree, so it is 0 minus 1, because in right subtree there is only one node, so which will end up with -1. So here you can see that the balance factors are within the range, and it is satisfying the rules of AVL tree. Now we don't have to perform any rotation operations, and we can just go for deleting the next node. So what is the next node to be deleted? 91, right? So let us delete 91 from this tree now. Deleting 91. Okay. So to delete 91, so we should find where 91 exactly is. 91 is right here in the tree, in the present updated tree, but 91 here, it is not a leaf node. So what is this now? So it is a parent node. And if it is a parent node, there are two possibilities. So the one is them having a single child, or it is having a multiple child. Okay. So here you can see 91 is having a single child, and even that child is not having any child nodes again. So what we should do in this case is we just swap them. So what should we do? We should swap 92 with 91, and then we can go ahead and perform the deletion of 91, because 91 becomes a leaf node. All right. So let us reconstruct it after deleting it. So I am go ahead and just construct the tree as it is. So this side of the tree is not affected, so I don't have to worry about this side of the tree, but the balance factors might be affected, that we should be keeping in mind. And here 92 goes up, and since it is replaced, the 91 is replaced with 92, the 92 comes here again, because 92 only the value is replaced, not it is that the value is swapped. So we are just going to replace the parent node with the child node value, and now since this node is not required for us, we can delete it directly. Okay, so I'm going to delete it directly now. Let me just write the tree here. So we have 70 here, and then we have 35, and then 30, and then you have 25, and then here you have 52, and then 40, and then 60, right? So here we are deleting 92 and 91, and we are left with 92 now. So now we will have a situation where the balance factors are impacted. So we will see how it is impacted. First we will compute the balance factors. So for the leaf nodes, the balance factors will be 0, and for this it is left minus right, so which is 0, and for this it is 2 left and 2 right, so which is 0 again. But whereas this is affected now, if you look closely here, so in left subtree we have 3 different levels for the deepest leaf node. So the height of the left subtree is 3, so 3 minus, and in right subtree there is only one node, so it is 3 minus 1, so where we end up with 2. Now the balance factor is not within the range of -1, 0 or 1. So now what should we do? We should try balancing this tree. So, but in which direction should I have to balance? So here you have to keep in mind this. So if the balance factor is a positive value, so if the balance factor is greater than +1, all right. So now in this case, what we should do is we should try and rotate them towards right side, because here you can see the less height portion in this particular situation is that the right subtree. So what we should do, we should try and push some of the nodes from left side to the right side. And what rotation do we call this? A left rotation. Because, sorry, not left rotation, a right rotation. My apologies. So this rotation we call as a right rotation, because we are trying to push them to the right side. Okay. So in this case, we will be performing a right rotation. Now we will go ahead and perform the right rotation in this case. And what if this is less than 1, or yeah, less than -1. So if it is less than -1, it is going to be opposite to this, wherein we will be performing a right rotation. We'll come across that situation also. Let us complete this step first now. So we will write, so now since we are performing right rotation operation between this particular nodes. So we will be performing rotation between this particular nodes. Okay. So which is 70, 35 and 92. So we will in this case 70 becomes the uh, in this case 70 becomes the left child, sorry, the right child of 35. So what happens now? So here we will end up performing right rotation. So here we will be performing rotation between this particular nodes, right? And it is really important to understand different rotations. So to understand different rotations that there are in AVL trees, do watch a video on AVL tree rotation operations. I have already made a video on that. And here I am going to consider this particular nodes to perform the right rotation, right? So why this particular subtree is because of this. So if the balance factor is a positive number which is bigger than 1, in this case we have to perform right rotation. And again there is a condition here. So if the left child of the affected node and the left grandchild of the affected node is having a positive balance factor, in that case we will be performing a right rotation. So if in case here, if we don't have 30 and 25 this particular nodes, that is when we are going to consider this particular subtree. Okay, do not confuse yourself, try keeping it very simple. So if in case in this particular example, if we haven't had 30 and 25, then here the balance factor would be something like a negative number. So in case of negative number, then we are going to go with the left right rotation, right? So which is left and right rotation. So here we have a positive balance factor for the child of this particular parent which is affected with the balance factor. In that case we will be simply performing a right rotation. Okay, so these conditions keep in mind. So now we will be performing a right rotation because we have a positive balance factor for the child of this affected node. So now what would be the updated tree? So the updated tree would be this. So we will be getting 35 as root node, and then 70 a new right child, and the left child of 35 would be 30 as it is. So the left child of 30 is 25, that also not affected, and right child of 70 is 92, that also not a problem. But here if you see, this particular subtree is kept hanging, right? So now what should we do? So this particular subtree should be connected to the new right child of 35. So what is the new right child of 35? 70. So for 70 we should be connecting this complete subtree. So in which side we should be connecting this particular subtree is to the left side. Why? Because for 70 this particular subtree is in the left side. So we can simply connect them to the left side of 70. So what are the nodes here? We have 52, 40 and 60. Now we should be calculating the balance factors because we are done with the rotation operation. 0 for leaf nodes, 0 for leaf nodes. For this node it is 1 minus 1 which is 0. For this it is 2 minus 1 which is 1. And for this it is 2 minus 3 because the deepest leaf nodes are this. 2 minus 3 will become minus 1. And what about this? This is 1 because 1 minus 0 is 1. Now here you can see this balance factors are within the range of minus 1, 0 and 1. So now this AVL tree is a balanced AVL tree. Now let us go ahead and perform the next deletion. So what is the next node to be deleted? We are done deleting 91. Now we should try and delete 92. Okay, so deleting 92. Let me just scroll some more. Okay, so here I'll write it delete 92. Okay, so to delete 92, first we have to consider the present updated tree. The present updated tree is this in the previous operation. So let us consider that 35, 30, 70, 52 and 40 and 60. Okay, and then we have 92 right here, and we have 25 connected to 35. We don't have to be worried about this subtree because we are not going to perform any operations on them. So here if you see 92 is the deleting node and 92 is a leaf node, and if it is a leaf node, we know what to do. We can directly delete this leaf node without any trouble, right? So let us go ahead and perform the deletion, and then we can check the balance factors. So after deleting 92, so the updated tree would be looking something like this: 70, 52, 40 and then 60. What do we have in the left of 35? 30 and 25. Now here if you see, we have a situation where the balance factors will not be within the range. So let us calculate the balance factors, zeros for leaf nodes, and for this node it is 0, and for this node it is 1, and for what about this node? So it is the deepest leaf node is 3, and here it is 2. So 2 minus 3 will become minus 1. But for this node, the balance factor is affected because there are two nodes in the left subtree, but in right subtree it is empty. So which will be 2 minus 0, which is 2. Again, the balance factor is a positive balance factor which is affected. So we will be performing a right rotation. Okay, but is that a right rotation alone or is that a right left rotation? That we should be checking. Here if you see, the child of the affected node is having a positive balance factor, so we are going to perform a right rotation alone. If in case if we haven't had 40 here, then we will end up with a negative balance factor for 52. In that case, we will be performing a right left rotation. Okay, so that I believe you have understood. Now we will be performing rotations on this tree. Let us complete the rotations. Okay, so the rotations that we are going to perform on this tree is the right rotation because the child of this affected node is having a positive balance factor. So let me just perform the rotation here. So the updated tree would look something like this. Not, why can I not write it here? Yeah, because we have space. Yeah, so I'll have root node as it is because we are not going to perform anything on it, and after we perform a right rotation, 52 will become the new root node. And what about 70? That will be pushed to the right side, and 40 stays as it is. But here we have a right child of 52, the previous right child, that should be connected to the new right child of 52, which is 70. So this will be connected to the left side of 70. And now we have 30 and 25 as it is. I hope you understood this step. Now we will calculate the balance factors and see if it is still affected or not. So the balance factor of this is 0 because we have the deepest, oh, I'm sorry, it is not 0, it is minus 1. Let me erase it, write it. So which is minus 1. And what about this? 1, 0 for this, leaf nodes are zeros, and for this it is 1. For this it is 1 minus 2, which is minus 1. And hope you understood why it is minus 1. We have 2 in the left subtree, but we have 3 in the deepest right subtree. So which is 2 minus 3 end up in minus 1. Now this is a valid AVL tree because we have the balance factors within the acceptable range. Now we will go ahead and delete the next node from the tree. So which is after deleting 92, then we should delete 30 now. Okay, so we'll delete 30 now. So to delete 30, first we have to consider the updated tree. So what is the updated tree now? So let us construct that now. So I'm just simply copying that 35, 30, 52, 40, you have 70 and then 60, and you have 25 to the left of 30. Okay, now this is the present tree that we have, and we should be performing a deletion of 30. Now here if you look closely, so 30 is not a leaf node and it is a parent node. And again, so a parent can be having a single child node. In that case, we can simply replace it and delete it. If it is having multiple leaf nodes, that is when you have to try and find the in order successor. For example, if I am asking you to delete 35 here, so here 35 is a parent node and it is having multiple child nodes. In this case, here we have to find the in order successor of 35. And what is the in order successor of 35 is very simple. In the right subtree, the smallest element. So here in example, 40 is the smallest element in the right subtree of 35. We'll simply replace 35 with 40 and delete this 35 directly. Okay, so here we are deleting 30 and delete 30 is having only a single child node. Now we don't have to worry about in order successor and all that. Just replace 30 with 25 and delete it. Okay, so what will be the updated tree? So the updated tree would look something like this: 35 and then 25, and then here there will be 25 because we are simply replacing the value, and then we have 50 to 40, 70, and then 60. Okay, now since we have 25 here multiple times, then we can simply delete it. Okay, so here I am deleting 25 directly. This is not 25 actually, though it is simply 30 which is replaced. All right, and that is why we can delete it directly. Now technically we are deleting 30 from the tree. Okay, now since we have deleted it, now we have to calculate the balance factors. So balance factors for leaf nodes will be 0, 0, and for this it is 1, and for this it is 1 minus 2, which is minus 1, and for this the balance factor will be impacted. Let us see. Left it is 0, but in right it is 3. So 0 minus 3 will be minus 3. Now we have a node with negative balance factor. Now in negative balance factor, what did we discuss? We have to perform something called a left rotation. But again we are confused here. Should we perform a left rotation alone, or should we have to perform a left right rotation? So here we will try and understand this. So here if you see, uh, oh, not left rotation, yeah, left rotation we will be performing, and in case if it is not, then we will end up in performing a right left rotation. This I believe you should understand. Okay, so here the situation is this. So we have a negative balance factor. Either we can perform a left rotation pushing them to the left side. If not, we will end up with right left rotation because it is in the right subtree, and we might also have the left subtree for the right child again. So we'll understand this step first and then we will go with this because you will be confused with this. So let us say in this case, so we have the 52, the child of 35. So here we have a negative balance factor. All right. So for the negative affected node, we have a negative balance factor. So in this case, we will simply perform this particular rotation, which is left rotation. Okay, simply a left rotation. And when will we perform right left rotation is in case if this is not having any of this left subtree. Let us say we don't have 70 or 60. So let me just erase this and make you understand. Let us say we have this now, and let me just update this. So what will be the balance factor in this case? A plus 1. So in this case, we will be ending up in doing a right left rotation because we don't have anything in the left to perform a left rotation or left rotation. We have a left child to the right child, and this is where we'll be performing right left rotation. Hope this you understood. Okay, so in this case we will end up performing right left rotation, but we have a right child's 252. So since we have this particular structure, so which is this structure, in this case we'll be performing left rotation simply. Okay, hope this you understood. So please rewind this step and do watch it carefully to understand when we should perform left rotation, right left rotation. Okay, do not worry, we will also end up in right left rotation in this example. I'll take you through that situation also. Okay, now let me just complete this rotation. So in this case we will be making a left rotation by making 52 a root node. So now 52 will become the root node for us, and 35 becomes the left child pushing it to the left side, and 70 stays as it is as right child, and for 70 we have a child node which is 60. So here if you see 52 is having a left child, which is 40, and the new left child of 52 is 35. So now what should we do? We should connect this 40 to the new left child of 52, which is 35. And which side we should connect it? To the right side. Why? Because so 40 is in the right side of 35. Not only that, so the simple trick here is that so you have to check the value of it and try satisfying the rules of binary search tree. And according to the rules of binary search tree, the bigger values should be in the right side. So here if you see 40 is a bigger value of 35, so we can simply add that to the right side. Okay, so here we have completed the rotation. Now we'll calculate the balance factors. Zeros for leaf nodes, and for this it is 1 minus 0, which is 1, and for this it is 1 minus 1, 0, and for 52 it is 2 minus 2, which is 0. Wonderful. So we have the balance factors within the range of minus 1, 0, and 1. Now we don't have to worry about balancing it anymore. Now we have deleted 30, and now we have to delete the next node, which is 70. Okay, now we will try and delete 70, deleting 70. Okay, so here if you see 70 is not a child node or leaf node, it is a internal node with single child. Now you all know what should do. We have to replace 70 with 60 and then delete 70 directly. Okay, so here let me construct the tree first. So we have 52, and after replacing it 60 comes up, and 70 can be deleted directly. I'm not writing it here. Okay, let me write it here because some of us will still be confused. So here we'll have 60, which is technically 70. Now we can perform deletion operation on it directly. Okay, so I'm just going to delete it by just erasing it. But in exam you cannot do it. You just have to construct the tree once more. All right. So do not be lazy in writing exam, because the evaluators will not understand the pain that you're going through. All right. Fine. So let me find the balance factors for this now. Zeros for this, all right? And for this it is 0, and for this it is 2 minus 1, which is 1, all right? So now we have the balance factors within the range. So now we don't have to worry about, balancing it anymore. So now we can go ahead and delete the next value, okay? So what is the next value? After deleting 70, now we should delete 60. Okay, now we will go ahead and perform deletion operation on 60. Let me just scroll some more. Yeah, so deleting 60. Okay, so to delete 60, 60 is a leaf node, I can directly delete it. So I am trying to construct it directly now. So 52 comes here, 35, 25, and 40. So now we have a situation, all right? So here if you see 52 is not having any right child, right? So then we have the affected node with the balance factors. So let me just write the balance factors first. 0 for this, and what about this? So it is 2 minus 0, which will be 2. Okay, so which will be 2. Now what should we do? We should try and perform a right rotation. I told you already, if it is a positive balance factor, we should be performing a right rotation. If not, a left right rotation. Okay, so when right rotation is, so when we have a left child to the left child, right? If we don't have a left child to the left child, that is when we will have to perform a left right rotation. In this case, if you don't have 25, then we will end up with left right rotation. Okay, so here we have a left child to the left child. Now we will simply perform only a right rotation. Okay, so in this case the updated tree would be this. So 35 becomes our new root node, and 52 is pushed to the right, and then we have 40 left hanging, so 40 should be connected to 52, and 35 is having a left child, which is 25. Now we have completed the rotation also. Now calculate the balance factors. 0 for leaf nodes, and for this it is 1 minus 0, which will be 1, and for this it is 1 minus 2, which will be minus 1. Now the balance factors are within the range of minus 1, 1, and 0. So now we don't have to worry about any more rotation operations. Now we will go ahead and see what is the next element to delete, which is 25. Right, now we will delete 25. Okay, so deleting 25. Okay, so to delete 25, I can delete it directly because 25 is a leaf node. Okay, so let me construct the tree after deleting it. 35, 52, and then 40. Okay, I already told you that I'll take you through a situation where we perform a right left rotation, right? So this is the right left situation. Let us first compute the balance factors, 0 for this and 1 for this, and for this it is 0 minus 2, which is minus 2. Now we have a balance factor which is negative, okay? And also if you see the child of the affected node, it is having only one child node which is in the direction of left side. So now we have a right left situation. If we had a node in this direction, okay, in this direction, if we had any node, then we will simply perform a left rotation. Okay, I hope that you understood. Now we have a situation wherein we don't have any right child to the right child to perform a left rotation, and this is why we will be performing a right left rotation. So right left rotation is a combinational rotation. If you don't know how right left rotation works or left right rotation works, please watch the video on introduction to AVL Tree and rotation operations. There I've explained all the rotation operations. All right. So now we will simply perform rotation between this grandchild and parent, and then we will perform a rotation in this direction between the parent and the grandparent. Okay, so now the tree would be updated into this. So 35 is left there, and 52 and 40 the rotation is performed. So what rotation we will be performing? A right rotation. Okay, and then we'll perform a left rotation. So after performing right rotation between 52 and 40, the tree would be changed into this. Okay, but still we should not compute the balance factors. We should compute the balance factor only after completing the both rotations. Now we will be performing a left rotation, and after performing left rotation the tree would change into this. So we have 40 and 35 here, and then we have 52, right? Now this is the updated tree. We have performed both the rotations. Now we calculate the balance factors. Okay, yeah, the balance factors are within the range. Now we don't have to worry about anything. All right, so now we are done with deleting all the nodes. We are done solving the problem also. Yeah, I hope you understood this problem. Now let me just take one more step to make you all understand when we will perform ALR rotation. Okay, but this is not in the tree, but just to make you all understand, I'm taking this extra step here, right? So let us say the tree that we have is this, the present tree. Okay, let us imagine we have a tree in this structure. So we have maybe say 37 here. Yeah, so now here the balance factor, if you compute the balance factors, would be this. So 0 for leaf node, that you know, and minus 1 for this, and for this it would be what? So it would be 2. Okay, now we have a balance factor which is positive, and in positive balance factor we will be performing something called a right rotation. Okay, that we already know. But here we have a situation where we don't have left child to the left child to the affected tree. That means we don't have any node in this position, so I cannot perform a right rotation. And what rotation is only possible for me to perform now? Only a left right rotation. This is when you have to perform a left right rotation. And just to make you understand, when we perform left right rotation, I have considered this example. Okay, now in this case left right rotation is a combinational rotation, and what should we do? First we have to perform rotation between grandchild and the parent. And what rotation we perform? A left rotation, and then we will get that in this particular alignment, and then we can perform a right rotation, okay, between this particular nodes. Now let me complete this. So the rotation goes like this. First we are performing left rotation between grandchild and the parent node. So we will be having 40 as it is, and then we will have 37 in the root position and 35. Now we ended up with this particular structure, the one which we want, and we should not calculate the balance factors until both the rotations are completed. Now we have to perform a right rotation, and in right rotation 37 will become the root node, 40 is pushed to the right side, and then 35 is still in the left side. Now this is how you perform a left right rotation in performing the deletion operation. I believe you have understood what I actually mean. Okay, in deletion operation also, if we end up in this situation, then you have to perform a left right rotation. All right, so this I believe you have understood. If you calculate the balance factors, they are within the range. Now we don't have to worry about any more rotations. Also do understand, so here in this example we got all the trees balance factors updated by performing a single rotation. But in some cases, if the question is complicated and if the examiner is giving you a complicated question, then you will end up having a unbalanced tree even after performing the rotation. So what should we do there? We have to keep performing the required rotations until and unless the tree is completely balanced. So this keep in mind. I believe you have understood this example problem and how you perform a deletion operation in AVL tree. And if you have any doubts, please do mention that in the comment section so that I will respond back to your questions that you have. And if you're stuck in any of the AVL tree problems like performing deletion operation or insertion operation, if you have trouble in understanding them, just mention that in the comment section. I'll come up with a video for solution to those problems also. And if you like the content of this video, please do like this video so that the video will be recommended to many students like you and many people like you who are willing to understand and who are having trouble in understanding data structures. And not only data structures, I'll be posting videos on many different topics like on programming languages like C, Python, or object oriented programming languages like Java, and also development oriented programs like topics like web development or, or data science and machine learning, or also mobile application development. Please do subscribe to this channel so that you will be notified with all the videos that I'll be posting in the channel. And do share this video if you feel that this video is worth sharing with your friends and who are going through this ADSA subject in their curriculum. And it is really difficult to understand data structures. I hope this video helps you in understanding data structures better. And thank you so much. Have a wonderful day ahead. Thank you.